Hello, everyone.
What up?
Nice to see you. I hope you all had a good Thanksgiving.
It was great. How was yours?
Pretty good. Pretty good. Got sick yesterday, but other than that, things have been pretty good. I actually got sick in the middle of class. I had to stop at like 8 minutes in. It was horrible. But I'm feeling a lot better now. Got to see a lot of friends and family over the holidays, so that was pretty nice. I hope y'all got to do something fun, even if you don't celebrate Thanksgiving. Maybe you at least enjoyed your time off from classes. Well, we've got about 12 people now, and time's actually started. So I'll start talking about what we're going to. Well, first off, I ask: does anybody have any questions before we get started on any past material or anything like that? One thing
I have a question.
The due dates on mastering is in some cases different from what it is on Canvas. So the ones on mastering are correct. It's just a real pain in the butt after you change dates on mastering, go back and change dates on Canvas. So trust the ones on Canvas. I mean, on MALAB and mastering right now, basically till the end of the semester, those dates should all be right. If you think one's a little too soon or something, send me an email and I'll let everybody know that I changed it if I agree with you. And somebody was
I did see on the MyLab and mastering thing that you had chapter 12 and chapter 13 conceptual. You had them twice. You had one as extra. You had two of them as extra credit, and you had two of them that weren't.
Okay. Thanks for letting me know that. I didn't realize it. I will. They're supposed to be extra credit because we didn't cover them. But you can do. There should be a homework and a conceptual for each of those. If you actually did one of the ones that wasn't, and you did the other one, I'll probably give you extra credit just for doing them twice. But be advised, my intent would be to erase the ones that aren't marked as EC for extra credit.
And I was wondering about the final exam. Mm-hmm. Is it going to cover everything?
Yeah, I make my exams comprehensive because that gives me another chance to give my students a lifeline. So if students aren't making very good grades and then they take a comprehensive final exam and they score a really good grade on it, like a 96 or a 97 or something like that. If their grade's working out to be a C, I'm probably not going to let them have a C. I'm probably going to give them at least a B and maybe even an A. So that's why I try to keep that's one of the reasons I try to keep the finals comprehensive. The other reason is, pedagogically speaking, it's really good for students to go back over and review everything they've done at the end of the semester. That second input of knowledge and working out the difficulties of the subject area that you've already covered actually helps you in the long run to retain and understand the information. A lot of times it doesn't click until that second time. So yeah, they will be comprehensive.
Okay, and you said you take the better of the two, only one of the two.
Not the better of the two. I only take the final if the final is better, but if the midterm was better, I won't take that. In other words, I will replace the midterm with the final, but not the other way around.
And will the final include chapter 43 too?
I'm a little undecided on that. I might make up just a separate test and maybe not cover 43 on the final. And that also might include 44 because I might go in. My intent is we have enough time. I think I can do 43 and 44. And the other option is 43 and then go back and do some nuclear physics. I don't enjoy that as much, but I do enjoy the 44. So I might actually leave those two off, but give them as another test, an online test, not a face-to-face or respondus test, but just a regular test. And then if I do that, I can feel justified in leaving it off the final.
And you said you say if you do good on the midterm and don't do that well on the final, though,
it still stays the midterm and the final grades. Yeah, so my ideal scenario is everybody peaks at the final. That's the best time to peak. And I don't want someone to say, well, I got this midterm in, yay, so I can just cool out, because that means you literally could ignore all the material since the midterm, and that's definitely not what I want.
All right.
So yeah, if you did great on the final, that's awesome. You're in a good spot and you're going to be well off for the final. The other good thing is a lot of times I take questions straight from the old tests. So if you're studying the old practice tests, or if you're actually studying the test that you took, because I think you can still see the version that you took when you took it for the online test, if you look at those, there's a good probability that a lot of those, that a lot of the final exam questions might be from those questions.
Okay.
Okay. Anybody else? All right. So elementary particles is chapter 43, and it's a whole branch of physics called high energy physics or elementary particle physics. And the reason why it's high energy we'll explain a little bit later, but it's kind of unfortunate that we put it at the end of 241 because it still needs you to understand some quantum mechanics, and we put our quantum mechanics at the end of 242. So I'll have to give you a little bit of the information that you'll use from quantum mechanics. The good news is you do need relativity, and we've had relativity, so that's nice. You don't need a whole buttload of relativity, but you need, the basic energy equation, and you need the idea of electron volts as energy. But what I'm going to do is I'm trying to explain to you the history of this as well as the founding of new particles and all that good stuff. And we'll start with ancient Greece. And in ancient Greece, the idea was they imagined, I went to grab my glasses, it worked out well, didn't it? Oh, see my pushing cat? So in ancient Greece, they had an idea. They said, okay, let's take a chunk of metal, say, and let's cut it in half. And then let's take half of that and cut that in half, and then half of that and cut that in half, and keep on doing that. What are the actual end results? And there was two scenarios they came up with. One was that you could do it forever, and that just didn't make sense to them. That was not physically reasonable. So they threw that result away. The other one is that you reach some level at which it became indivisible. You could no longer divide it. And the Greek word for divisible is tom of some sort, and then the prefix that you put on it to say un or indivisible is a, so they called it the atom, the atom. Okay, and we have since learned obviously that that's not the indivisible thing that we thought it was, but that was the idea of an elementary or a fundamental particle. In that case, you'd have one elementary or fundamental particle for each element that we know of, and we're up to about 130 now, I think, that we've, and most, a lot of them are not stable and that sort of thing. But the definition also varies from elementary versus fundamental, and I'll never ask you to tell me the difference between them because I never remember it myself. I look it up the time that I need it so that I don't make a fool of myself when I'm writing something, and hence it might appear on a homework, it might appear on a quiz or something like that, but it's never going to appear on any of my tests, so don't worry too much about that. What your book right now is defining as fundamental particle is any particle that doesn't have any structure. So in that sense, they're talking about like it doesn't have a physical size. It should be really truly a point particle. I always thought of the elementary particles as the ones that aren't made up of other stuff. So that sort of is a very much equivalent definition in many ways. So to date, what we've discovered is the atom is very much divisible. And in fact, it is the elementary smallest element of a given element. So for instance, all the elements on the periodic table, if you cut them in half over and over and over again until you get something that can't be divided anymore, except for becoming another substance, then you've reached the atom. So in that sense, it is indivisible, but not in the true sense. You can break it apart. Similarly, if you have a compound like water or sodium hydroxide, you can cut that in half over and over and over. And once you get to an actual molecule of sodium hydroxide, if you were to break that apart, it would no longer be sodium hydroxide. So in that sense, it's also indivisible. But again, you can still break it up into protons, neutrons, electrons, that sort of thing. So what we now have as elementary particles, you might think, is the individual parts that make up the atom. And that would be the proton, the neutron, those are both in the nucleus, and then the electrons, which are in some sense orbiting around the nucleus, or at least the probability of finding them at some point in space is a maximum, as if it is in some circular or elliptical type orbits around the actual nucleus. Well, from that group, it turns out that the protons and neutrons are actually not elementary. They are made up of other things. They're in fact called baryons. And in fact, baryon is the word that they use for anything that's a nucleon, but then they discovered other baryons, and those are not part of the nucleus, but they're still called baryons. So the proton and neutron are each made of 3 quarks. And then there's other types of particles that are only made of 2 quarks, a quark and an antiquark pair. And the quarks seem to be fundamental particles. In other words, they seem to be something that are infinitesimally small, have no structure to them, and are definitely not made of anything else. Electrons turn out to be, as best we can tell, a fundamental particle as well. It does not appear to have any physical dimension. We've measured its upper limit of how big it is, and it's way smaller than the nucleus of an atom by a long shot. So we think it is truly a point particle. And then we have basically, after all this is said and done, what we're looking at now is we have fundamental particles are things called the leptons, which are like electrons. Okay, one of them is the electron, and then it has a neutrino and electron neutrino specifically. Then there's a muon, which y'all learned about in relativity, and that's like a electron. It's a mu minus, in fact, so it's even similarly charged as the electron, but it's 207 times more massive than the electron, and it has an associated neutrino with it, a muon neutrino. And then additionally in the lepton group, you also have a tau particle, and the TAU, by the way, the Greek letter tau particle. And that, I think that's on the order of like 3,000 times as massive as the electron, but it again behaves like an electron, and it has a associated neutrino as well, the tau neutrino. So those are the fundamental particles called the leptons. Then the fundamental particles, of course, are something called gauge bosons. And this is really weird, but somewhere along the line, specifically with Yukawa, Hideki Yukawa, suggested that the strong nuclear force was actually not really good to be thought of as a force, but rather as an exchanging of particles in a very small, finite amount of time, very, very small amount of time, though. And he even predicted how massive that particle would be. And later we found out that that particle was in fact a pion, but we later learned out that he was a little bit wrong. That pion is not fundamental. It's made up of smaller particles as well, which turn out to be the W and the Z boson, or excuse me, the W and the Z boson. My fault. That's the one for the weak nuclear force. The strong nuclear force turned out to be a different particle. So there's these particles now that we picture as if those are being exchanged between particles as opposed to forces. So you knew, like we learned in gravity, that you had a mass, say the sun, and then you had another mass out here, the earth. And if you multiply those masses and then divide by the square of the distance between them, and then multiply it by the gravitational constant, you got the magnitude of the force of the sun on the earth, right? Well, I told you how no one liked that, including Newton. And in fact, what we ultimately did, and we didn't, I hinted to you this, but I didn't actually express it to you. But if you take that force, that G M Earth, M Sun over R squared, if you take that force and divide out the mass of the Earth, then you just get G, the mass of the sun, over R squared. And that's what we would actually call the gravitational field of the Earth. So the gravitational field of the sun. So it's as if the sun is in space and has created a field around it. And what do we mean by field? We mean if you take any XYZ position in space, this field assigns to it a quantity in newtons per kilogram that is a vector quantity. In other words, that particular point in space will have a direction and a magnitude. And then if you take that magnitude and you multiply it by the mass of, say, me, then you end up getting the mass the force of gravity on me from the sun at that particular spot. If you multiply it by, instead of my mass, the mass of the Earth, and you put it actually at the position of the Earth, then you get the actual mass or the force on the Earth due to the sun. So that's the way we sidestepped the idea of action at a distance. We created a field and assumed it existed, and then we found all these results that were consistent with it existing. So we stuck with it. We did the same thing with electricity and magnetism. They ended up being not only similar fields, but in fact the same thing. So we had this idea of a field, and that took care of action at a distance. Now, what's going on with this gauge boson thing is even weirder. So you can imagine, for instance, two protons coming towards each other like this. Okay, so the two protons come towards each other like this, and you know they're both positively charged. And though you haven't had 242 yet, you probably know that like charges repel and unlike charges attract, just like north poles of a magnet repel and north and south pole of a magnet attract. So the same thing with charges. Like charges repel and unlike charges attract. So if it's a proton and electron, they would run towards each other, but since it's a proton and a proton, you'd expect them to do this. Well, you can think of that as this proton right here is creating a field all around it. And then this proton coming over here is affected by that field and feels a force pushing it outward. But similarly, this proton's causing a field and this proton's feeling that field, so it gets pushed outward as well. And that's the way we examine the force. But what we're saying with these gauge bosons is, imagine this scenario. Imagine these photons are coming close to each other, and spontaneously the proton emits a photon. The proton emits a photon, okay, the particle of light, the photon. So in doing so, just like an ice skater who's standing on his ice skates in the middle of a frozen pond, if he were to shoot a shotgun, he's going to recoil backwards on the ice skates because there's almost no friction. And if he's, balanced enough so that he don't flip over, and he's going to actually slide backwards, accelerate backwards. So the same thing's going to happen when this proton emits a photon. It's going to recoil, and then that photon hits the other proton, and it's going to hit it and recoil this way. So you get the same result, whether it's this particle being exchanged back and forth or not. If you happen to have an attractive force, it's sort of like they are stealing photons from one another. So this proton, for instance, might grab a hold of this photon over here and pull it, and that causes this electron to move this way. And similarly, when it pulls it, it has to recoil by going this way. So that forces the proton and the electron to attract each other. So that's the modern way that we think about forces in something called the Standard Model, which was independently created by Sheldon Glashow, who I've met a couple of times, not a pleasant person, but obviously a bright person. Steven Weinberg, I've spoke with a couple of times. He just passed away like a few months ago. That was a great loss because he really was a kind person, like literally answering an email from a lowly physics instructor at a community college in Virginia Beach, multiple times answering my emails. So really a sweet guy. And then a guy by the name of Salam in India. All three of these guys came up with the Standard Model independently. And the cool thing about Sheldon Glashow and Steven Weinberg, they were both students in the same schools in New York City through public schools. So can you imagine, one, they're super competitive, as are all upper echelon scientists. They're super competitive, but can you imagine how awful it would have been to be in a class where two Nobel laureates are both in the same class through middle school and high school? But that's kind of neat. So anyways, they came up with a Standard Model, and that sort of explains all that. And it puts all the forces, except for gravity, it couldn't do gravity. It puts all the forces in a way that we can imagine them as an exchange of particles instead of fields and all that good stuff. If we ever find the gauge boson for gravity, that will be called the quark. Or excuse me, quark. Where's that? I don't even know where that word came from. It would be called the graviton. Okay, I think I was thinking of something else, but anyways, the gluon is the one that holds the actual strong nuclear force, and the W and the Z bosons are the ones that hold the weak nuclear force. The electromagnetic force, on the other hand, just like I just showed you, was the photon. And the photon, of course, is massless, but that's what has to happen, as you'll see later. If the force has an infinite range like the electric force does, then the particle must be massless. And we'll see why that's the case in quantum mechanics from a quantum mechanical standpoint once I teach you about the quantum mechanics. So this is what all the sort of fundamental particles came out to be. We've got leptons, we've got quarks, and we've got gauge bosons. Okay, and the quark can build all these other things, and of course the leptons can combine with the baryons that are made of the quarks, and they can make atoms, and then atoms come together to make molecules. But in addition to that, in 1928, a guy by the name of Paul Dirac, who's probably as close in real life to what Sheldon is on Big Bang Theory as any scientist that ever lived. He seems to be very much on that Asperger type spectrum scenario. So much so that one of my master's advisors was in a class of his, or in a lecture of his one time, and someone asked, he was giving a lecture, and the student asked, Professor Dirac, could you please tell me why does the electron have spin? And Dirac just starts basically repeating exactly what his book on quantum mechanics says. I mean, verbatim off the top of his head. And she said, well, professor, I was trying, I understand that sounds just like what you said in your book, but I'm trying to get an understanding of why it has spin. And he said, well, if it could have been explained better, I would have put that in the book. So little stuff like that. And they'll, he was one time giving a presentation, and the host said, does anyone have any questions for Professor Dirac? And they said, one of the students raised their hand and was called on, and he said, I don't understand how you got from here to here in this derivation. And he just sat there with a long pause of silence until finally the professor said, the host said to the Professor Dirac, I think the student wanted you to explain that step there. He said, oh, I'm sorry, they didn't ask a question. I just thought they just wanted to point out that they didn't understand something. So this is very much a person that has some tendencies like that and was very brilliant. This is really a sad scenario.
That's funny.
Isn't it? It's crazy. It's really a sad scenario though. He had an older brother, and you imagine how hard it is when one brother outshines another, or one sister outshines a brother, or something like that. Well, this poor guy, his brother ended up taking his own life. It was just too much to live for. This guy was like super brilliant. Like at age of 5, he's learning calculus and crap. It's not quite that bad, but it is pretty bad. So he creates this equation. Schrodinger had our equation for quantum mechanics, and it was based on conservation of energy. And it basically came from this operator acts on the wave function and spits out the kinetic energy. This operation acts on the wave function and spits out the total energy. And this operator, which is just the formula for the potential energy, acts on the wave function and creates a potential energy function. So kinetic energy plus potential energy equals energy. That's the Schrodinger's equation. Well, the problem is he used p squared over 2m for the kinetic energy, and that's not relativistic quantum mechanics. That's just plain classical mechanics. So Dirac immediately saw that. Dirac publishes his version, which is relativistically correct and is in fact the correct equation. It's Dirac's equation, but you don't have to use it because, except for extremely high speeds and extremely large masses, relativity is not that relevant. So anyways, he creates this equation. It's right in some sense, but people immediately start complaining, no, that this equation can't be right. It's got negative energies, and negative energies are meaningless. And he literally said, no, the equation is right. There must exist particles that we've never seen before that are in states that are inaccessible to us, and that should be called antimatter. And occasionally they should come out of that state we can't reach, those negative energy states, and combine with actual matter and annihilate itself if it's a similar particle, but still act like the other particle in every other respect. So he literally predicted the existence of antiparticles and antimatter based on his belief that his equation was right, period. No ifs, ands, or buts about it. And lo and behold, in 1932, 4 years later, they knowingly detected the positron, which is the anti-electron. Okay, so that's brought in a whole new thing, because it turns out that every particle has an antiparticle, and some particles are their own antiparticles, and they're called Majorana particles, Majorana, after Etos, or I think I can't remember the first name, but after a famous physicist who just disappeared one day. So we've got those types of particles too now in the bevy of all the particles. So to get started explaining all that, we need a little quantum mechanics. So I'm going to start off with showing you that. So let me turn our document cam on and get started with that. Does anybody have any questions on what I've said so far? Okay, so I've explained this before, but basically in the late 1800s, early 1900s, everybody thought physics was finished. We figured it all out. We got Maxwell's equation that explains everything from electricity and magnetism. We have Newton's laws of motion that explains everything mechanically. We're really just a matter of studying all these problems and see if they're actually right to the 7th decimal place instead of the 3rd decimal place. And that's what most people would have thought, but it turns out there was a few big experiments that were screwing up things. One of which was the photoelectric effect, one of which was called the ultraviolet catastrophe, and another one was the spectrum of gases, basically. So the first one was tackled by Planck, and Planck basically said, hey, I know that particles are metals or solids or anything like that, if you make a plot of energy versus frequency, and that's the energy put out by an object at such and such a color, that's what the frequency could mean. We knew basically that there was a gradual line reaching up to a peak and then a sharp fall like this, not quite vertical. I drew a little too vertical there, but it should never, it should really be a function. So it has to go a little bit further like this. Okay. And he wanted to explain that curve, and he was using a technique that scientists used often, and that was basically pretending like this variable f was continuous, or this variable e was continuous. That's what it really is, but he tried to pretend like it was broken up into little truncheons of frequency. So like energy could be a number times frequency, where that number had to be an integer. So you couldn't have 1.5 times some number times frequency to get the energy. You have to have 1 times some number times frequency, 2 times some number times frequency, 3 times some number times frequency. And in fact, the process requires that you then go back and do a process to make it a non-discrete variable back into a continuous variable. But every time he did that step, it turned out to make the result bad. So he finally just said, screw it, I don't know why, but I'm going to have to go on the assumption that energy is equal to n times some constant h times frequency, where n is the integers 1, 2, 3, ... and nothing else. So this is the quantum hypothesis. And with that quantum hypothesis, we found that h, which is called Planck's constant now for obvious reasons, is 6.63 times 10 to the negative 34th joules seconds. And we can put in other units if we want, like electron volt seconds and stuff like that. But anyways, this is Planck's constant. But notice it's 0 followed by a decimal point followed by 33 zeros and then a 663. So obviously we have very good reason to have not noticed before, because the energy difference from 1 HF to 2 HF was really, really small, right? So we would have never even noticed that. But that was the quantum hypothesis, and that gave us the equation E equals HF, which if you use c, the speed of light, is equal to lambda times frequency. Then you could also see it's equal to hc over lambda. So that's an important result that we make use of from time to time, and that's why I introduced that to you. Another one was the photoelectric effect, and that's where Einstein basically took this E equals HF and used that to be the energy that's allowed when radiation or light hits a pure metal. And this was the monumental first paper of quantum mechanics. And then Einstein's photoelectric effect was the second paper, where he made use of this and made perfectly clear why the photoelectric effect occurs. And basically the photoelectric effect is when you shine light on a metal, it will actually create a current in that metal. But it acted in a weird way. It didn't act like it should. There was no time delay. There was no increase by brightening the light. It increased, but by increasing the frequency, stuff like that. So Einstein did that one, and that was the photoelectric effect. But again, he's using that. And the third one was the spectra, and that's where we got the Bohr model of the atom. So the photoelectric effect that was explained by Einstein. And in fact, that's what he won the Nobel Prize for. And oddly enough, it was in that same year, 1905, that he wrote Special Relativity, that he explained Brownian motion, which proved the existence of atoms, that he wrote E equals mc squared, which showed how the sun worked. All that stuff came in 1905. And he ended up winning the Nobel Prize, of course, for this one. The next one was the spectrum. And basically what that meant is when you take a gas and you put it in a tube, a pure gas like hydrogen, helium, mercury vapor, anything like water vapor, all that kind of stuff. And then you suck all the air out of the tube, put the gas in there at a fairly low pressure, and then run a little electrode in each side of the tube, and then put a high voltage on it. Lo and behold, it'll glow. That's what neon lights are that you've seen in stores and stuff like that. Well, the weird thing is, if you take that light coming from that neon tube and you send it through a prism, for instance, then it'll spread it out, and you'll get parts of a rainbow, but only little distinct lines of certain colors. And those certain colors change from one element to another, or to a compound and all that. And that was a big deal. And that was, of course, solved by Bohr. And that's the Bohr atom. And those three ideas were what created quantum mechanics. Now, another guy comes along by the name of Heisenberg, and Heisenberg's a student of Bohr's. Just about everybody's either a student of Bohr's or someone related to Bohr. Bohr's really the person that created this, and he didn't just do the Bohr atom and that was it. He really fathered quantum mechanics along and made it what it is. But anyways, Heisenberg comes along and he comes up with an entirely different version of quantum mechanics based on selling meth. No, that's a different Heisenberg. Heisenberg, and then Schrodinger too. They both make equations for quantum mechanics, but Heisenberg's is based on, it's a really abstract thought. It says, okay, hey, I can only measure certain variables, so I only care about those certain variables. And those certain variables are related by a process of multiplication of matrices. And by the very fact that you oriented that way, we get the uncertainty principle, which is another thing we need. And one version of that is the uncertainty in the x component of momentum, p sub x, times the uncertainty in the position in the x direction is greater than or on the order of h over 2 pi, which is a quantity we call h bar, by the way. That's one version. Another version, the one we're going to use here, is delta E, the uncertainty in the energy, times the uncertainty in time is greater than or equal to h bar, again, or h over 2 pi. I got ready to do both. So h bar or h over 2 pi again. So those are the uncertainty principles, and they came naturally out of Heisenberg's form. It turns out the Schrodinger equation, del squared h squared over 2m psi plus v psi equals I h bar partial of psi with respect to t. That's Schrodinger's equation. It turns out when you solve this, notice there's an I in it. When you solve this psi obeys these principles. If you do the process of calculating what the momentum in the x direction is and what the actual x value is and calculate their uncertainties, you get the exact same thing. And in fact, these were later shown to be equivalent. Okay. Now, Bohr's model didn't make any sense. He just basically said, hey, I need to quantize something. And he quantized angular momentum of the atom, of the electron. He imagined the electrons in the Bohr atom to be standing waves, so that the distance around the lowest orbit was exactly one wavelength. The distance around the second lowest orbit was 2 wavelengths, and then 3 wavelengths and 4 wavelengths. That actually turned out to be what it was related to. But he didn't do that. He quantized angular momentum, which made no sense, but he ended up getting exactly the equations that we needed from the spectrum. What then made that make sense is a guy by the name of de Broglie. So it's Louis, L-O-U-I-S, D-E-B-R-O-G-L-I-E, and I have no idea if I'm pronouncing his name correctly. Louis de Broglie comes along and says that basically he says the universe is beautiful, science is beautiful, it's elegant, it's pretty, there's no way it's ugly, and because of that, I believe this. And that sounds really stupid, but that really is more or less what is going on there. Scientists have a belief that that is almost always proved true, that the universe is elegant and beautiful. And one example is, for instance, there was this famous diagram that existed, and it had a particle here on the diagram. It had a particle here, and it had a particle here on the diagram, and it had a particle here on the diagram. And that bothered a lot of people because that's an ugly drawing. You know, if I were to put another particle right here, it would be a pretty drawing, and I would be happy. And from this, Murray Gell-Mann and Richard Feynman essentially postulated the existence of another particle, And from that graph, they were able to define certain characteristics of it. And then lo and behold, that particle was found, and it was the omega minus particle. So that's what I mean by symmetry and beauty in science. When we find something that's not beautiful, many times we find out that it's wrong. Well, de Broglie had the same scenario. What we had discovered by all this stuff was that light, which we always traditionally considered a wave, until that brief spurt where Newton said it's corpuscles or particles of light, and he made up all of optics. Then after Newton died, Huygens and all these other people did the exact same thing, treating light as a wave. Maxwell as well did this, and in doing so, they found out exactly the same equations that Newton did for optics. So we had matter, or excuse me, we had light, which was traditionally waves, but now has non-traditional, has particles. Well, then you come to the idea of what about matter? Well, matter was traditionally particles, and that looked like a real asymmetry. There's no way light has wave and particle characteristics, which are like matter, and matter doesn't have both. So he hypothesized wave material. Okay, so that was literally what he was going on. If you just do a unit analysis, you could say P, momentum, classically, of course, is kilograms meters per second. We know Planck's constant is going to come in there, and unit wise, that is going to be joules times second, and a joule is a Newton meter. So it's a Newton meter times second. So that becomes kilograms meter per second squared times meters times seconds. That seconds is going to cancel out with that one, and I just get kilograms meters squared per second. Okay. And we want wavelength, which has units of meters. So if you say, okay, P to the M is equal to H to the N times lambda to the Q, then you could say, okay, well, that means P, which has units of kilograms meters per second, would be kilograms to the M power. I really shouldn't have used M since that's on there. Let's change that to X power. So that's kilograms to the X power, M meters to the X power, and S to the X power is equal to kilograms to the N power times meters to the 2N power over seconds to the N power times, now we just have meters to the Q power. Now we look on this and we see this side we got kilograms to the X, this side we got kilograms to the N, so X equals N must be true. This side has M to the X and M to the 2N, so X equals 2N. Now it gives us that in fact N, or excuse me, X is equal to 2N. Wait a second, where did I go from? X equal to N. Oh, excuse me. That's what went wrong. Hold on. Now on this side, we have X to the M to the X power. Here we have 2N plus Q. So X is equal to 2N plus Q. With that, you got X to the 2N plus Q. And we know X is equal to N. So I'll say X is equal to 2X plus Q. And that gives me X is equal to negative of Q. Okay. And then you could have the S, and in that case, it seems that S to the X is equal to,
We can't see
yes,
it.
excuse me, okay. S to the X is equal to S to the N. So again, we find that X is equal to N. So lo and behold, what we see is what can work is letting X equal 1. Then you get P is equal to H over lambda, because Q is going to be -1. And that's exactly what de Broglie said was the wavelength, or how you could find the wavelength of a particle. Okay, so you can look at it that way, or you can look at it as lambda is equal to H over P, and that was the de Broglie hypothesis. Okay, the problem was he wrote that in his PhD thesis, and he was doubly noble from 2 different family lines, and the PhD advisors are like, oh, this guy's really bright, but this is some crazy crap he come up with here, and almost no reason for it. So they kept really trying to put him off. Luckily, this was in the era of 1917, 1918, somewhere along there. Actually, it was a little bit further than that. But Einstein was touring, and he visited the university that he was at, and they asked him to look at his thesis, and Einstein said it was one of the most brilliant things he'd seen in a long time. So they immediately gave him his PhD. So these are really the quantities we need. So now that we've given that introduction to quantum mechanics and all that good stuff, we only got what we got a little bit more than 30 minutes left. So yes, someone had a question, Tristan, maybe?
Yes. What does P stand for, units wise?
Yeah, P is the momentum. Now, classically, we treat that as mass times velocity. That's why I wrote it up there. But it turns out this also works when you replace that with relativistic momentum.
Okay.
Okay. All right. So that is what the big deal is with quantum mechanics at this point. And we start to want to understand what matter is made of. And here's the scenario. So let's take for a second and consider we want to figure out the shape of some object. Okay. So let's imagine an object has a 4-foot by 8-foot sheet of plywood on top of it. And then dead center in it is this little shape like this. Okay. Now, if you look at it, it's such a long distance. You can see that, it's about an inch wide here, about 3/4 of an inch wide this way, about 1.25 inches this way. But that's pretty much all you can tell. So you're given the task of discovering the shape of this. So what you might think of doing is shooting marbles at it and following the marble's trajectory, and then using that to work backwards and figure out where the particle's edge or where the thing's edge were and what their angles were. So you can do that. You can say, okay, well, here's a marble, and this marble comes shooting in like this, and then bounces off and comes off like this. And you got this trajectory, this trajectory. You can trace them back in space and say there's obvious an edge right here. And then you can say, well, the angle of incidence has got to equal the angle of reflection. So I cut this in half and make it perpendicular to it. And then you know that that surface right there has that angle to it. And you keep doing that, and you end up getting an idea of what the shape is. But you're never going to figure out this, because there's no way in heck that marble is going to be able to fit inside of there. So what you try is a BB, and a BB can make out some of these corners a lot better, but it still can't get in there. And then you go to say maybe buckyball, microscopic buckyball that's literally the size of micrometers. You start firing that, and then you can get closer. So what you see is the smaller the object is that you're probing it with, the smaller the details you can get. So the size of the details that you can get are on the order of the size of the probe. Well, that happens to be the same thing with regards to light. If we want to shine light on something and see what it's shaped like if we want to see what, say, an electron shaped like, we have to hit it with something whose wavelength is comparable in size. So the idea of that is, oh, wait a second, wavelength is equal to H over P. And if I want something to have a really small wavelength, then P must be large. So that's the fundamental idea of particle accelerators having to shoot things at such a high speed. So they knew at that time, you know, when they, this is say the 1930s through the 1950s, they knew they needed to probe the nucleus and various other things with high energy particles, because the higher the energy, the smaller the wavelength, and the smaller the wavelength, the more details you could get. So what was first come up with was something called the cyclotron, and it was created by, and he has his picture here, but it was created by Ernest Lawrence. And if you ever heard of the Lawrence Livermore Laboratory, that's named after him. But E.O. Lawrence is the guy, and his picture's on page 1166. So what he did was he actually said, let's create something to accelerate particles. And what he did was, when he realized that then he'd go in a circle due to magnetic field, that the frequency at which you needed to flip the electricity back and forth was independent of speed, so he could make an accelerator. So his accelerator was called the D's, and basically it was 2 half circles that were like, they're actually more like canisters. So like they were shaped like this, and they would be put in a vacuum. And then here's the other D, which looks the same, but it's the opposite orientation, like that. And what happens with that is you drop a particle dead center, and then you apply a voltage across this so that this side's positive, this side's negative. Let's say it's a proton. Well, if it's a proton, what's going to happen is the proton is going to go this way. And as it starts to move, it turns out that the force, you don't know this yet, so I got to give you this too. The force acting on a charge Q with velocity V due to a magnetic field B is QV cross B. So you see this force is actually going to be perpendicular to the velocity and to the magnetic field. And in fact, with a positive charge, we could basically say that if the magnetic field is up, then QV is this way, magnetic field's up, and then that would make it deflect downward. But if the magnetic field's down, which is what I'm going to choose here, and uniform, then we get something really nice that happens, and you'll see in a second. What's going to happen is that's going to cause it to go in a circle. And then once it goes across here, you flip the polarity of this, so it'll now be attracted to there, and that little spot will speed up the proton, and then the proton will have to make a bigger radius circle, and then it gets sped up again, and the proton will have to make a bigger circle, and it'll get sped up again, and the proton will make a bigger circle, and it gets sped up again, and then a bigger circle, again, bigger circle, again, bigger circle, bigger circle. So each time it goes through that gap, it's actually getting a boost in velocity until finally it shoots out here and hits the target. So that was a super mega cool idea. And if you flip this positive and negative at just the right frequency, then everything's golden. Well, we've set this up such that QV and B are perpendicular. So we know that Newton's second law, the summation of forces equals mass times acceleration, for something going in a circle is just going to be QVB is equal to mv squared over r, where r is whatever the radius of the circle is at a particular point, right? So we can actually cancel out this v and solve for velocity. We'll get the velocity is equal to q times b times r divided by the mass. So a heavy object is going to obviously go slower, and of course would require a larger radius and so on and so forth, but that's the velocity. Now, if you want to work out the frequency of this, this is an equation you will need, by the way. But if you want to work out the frequency of this, maybe we work out the period first. So the period is the time required for one cycle. And we know that velocity is equal to distance divided by time. So time should be equal to distance divided by velocity. Well, in one cycle, the particle is going a distance of 2 pi r, right? So I'll write 2 pi times the radius, and then the velocity is q b r over m. So I get that 2 pi m r is equal or over Q BR is equal to the period. Notice the R's cancel out. So I now have that the period, which is something also useful, is equal to 2 pi m over QB. So that's another valuable equation. Now, if I want the frequency, we know frequency is 1 over the period, and this is really the rate at which you flip these back and forth. So in other words, take out that battery, put in a AC signal that looks like this, and as long as you make the frequency match this frequency, then it will always cause these particles to accelerate. So that turns out to be QB over 2 pi m, and that's the cyclotron frequency. So that's the cyclotron frequency. And that was a really good first accelerator. They never really made them more than maybe 1 meter across, and they were mostly just used to accelerate protons. So let's try an example. First off, I'd like to know what is the wavelength of a 2.0 GeV electron. Okay, so what is the wavelength of that? So we're going to use P is equal to H over lambda, or lambda is equal to H over P. We're going to use the de Broglie hypothesis. All right. Now we know, hopefully you remember from relativity, that the mass of the electron times c squared gave us 0.511 MeV, right? So this is way bigger than the rest energy of the proton, of the electron. Because of that, we know two things. One, we know that we have to use relativity. So whenever the energy, and by the way, this is when they say the energy of it is such and such, that always means kinetic energy. That was something that I always was confused about through undergraduate. And then finally I realized, okay, yeah, they're always, when they say a certain energy, electron, proton, or whatever, they mean the kinetic energy. So when the kinetic energy is comparable to the rest energy, you have to use special relativity. And then also, since this is the case, we know E squared is equal to P squared C squared plus M squared C to the fourth. This is on the order of 0.5 MeV. And this is in fact 2.0 times 10 to the third MeV. So this part right here is very close to 0. So we can say that in fact, P is equal to E over C. That's a very good approximation. So there we can say lambda is equal to H over E over C, which is actually HC over E. And when I do that calculation, I get 6.63 times 10 to the negative 34th joule seconds times 3.00 times 10 to the 8th meters per second over 2.0 times 10 to the 9th EV.
Can you scroll down?
Yes, thank you. But since that's an EV, I got to convert it. So it's 1.602 times 10 to the negative 19th joules per electron volt. So that's actually converting it back to joules, and then this joule will cancel out with that joule, and this meter per second will cancel out with a second. So I just get meters. And when I do that, I end up getting, I think I actually already worked that before. I'll double check my math because, yeah. Where's my calculator? Okay, there's my calculator. So I'm gonna put this in my calculator. So I'm gonna say 6.63 e to the negative 34 times 3 e to the 8 divided by, I'll use parentheses, 2 e to the 9.
I think you typed in times e to the negative 31.
Oh, did I? Oh yeah, thank you. Nice catch. That's the actual exponent for the mass of the electron, not that. Okay, so now I'm going to do, thanks for catching me on that, 1.602 e to the negative 19. And that gives me 620.8 times 10 to the negative 18 meters, which I can call 6.20. By the way, that's 2 extra sig figs. So I'm going to say 6.21 and just carry 1 extra sig fig times 10. Notice I divided this by 100, so I got to multiply that by 100. Multiplying by 100 means multiplying by 10 to the positive 2, so that's 10 to the negative 16 meters. So that's about a factor of 5 smaller than the nucleus. So yeah, an electron at 2 GeV can be used to probe the size of the nucleus. So that was example 1. Now let's try example 2. And this was one where I'm going to use the stuff about the cyclotron. So in this case, what I want to do is imagine a cyclotron with R equal to 0.50 meters and B equal to 2.0 Tesla. What I want to do is calculate the frequency. So what is F? That's going to be part A. Part B, what is velocity? And part C, kinetic energy. Okay, so that's what I'm going to try to do. So we know the frequency, according to that equation that I derived for you a second ago, that's QB over 2 pi m. And as I told you, the cyclotrons are usually used for protons. So I'll say for a proton. So now I'm going to put in 1.602 times 10 to the negative 19th. Remember, the charge of the electron and proton are the same, except the proton's positive. The B is 2.0 Tesla. You haven't had enough electricity and magnetism to break down this unit, but just trust me, it does work. All this is going to be divided by 2 pi, and then times the mass of the proton, which I believe is 6.67 times 10, or 1.67, that's it. 1.67 times 10 to the negative 27 kilograms. So I'll put all this in and I'll get, so y'all can catch me if I do something stupid. So I'm going to say 1.602 e to the negative 19 times 2 divided by parentheses 2 times 3.14159 times 1.67 e to the negative 27, and that gives me 30.5 hertz, or excuse me, 30.5 times 10 to the 6. So that's 30.5 times 10 to the 6 hertz. That's basically, if such a station existed, that would be 31 FM or 30.5 FM, because the FM is actually measured in megahertz, which is what that is. So that's the frequency that you'd have to oscillate that at. If I want the velocity, which I do, the velocity turns out to be, and that was part A. B turns out to be Q, B, R over M. I'll put an A here. And that's going to be 1.602 times 10 to the negative 19th coulombs times 2.0 Tesla times 0.50 meters. You can see that just cancels out each other. And then I'm going to divide that by 1.67 times 10 to the negative 27 kilograms. And that basically looks like the same thing as this, except 4 pi times it, but I'm going to go ahead and put it all in anyways. So I'll say 1.602 e to the negative 19 times 2 times 0.5 divided by, I don't even need parentheses here because there's only one thing, 1.67 e to the negative 27. And this gives me 95.93, 2 extra sig figs again, times 10 to the 6th meters per second is equal to the velocity. So that's part B, okay? Now what we want to do is figure out what that kinetic energy is. Let's assume for a second that that's going to be classical. So K is equal to, and I'll put a question mark over top of that, 1/2 mv squared. If we find out that that kinetic energy is nowhere near the rest energy of a proton, by the way, the rest energy of the proton is something like 658 MeV per c square, or 938, sorry, equal to 938 MeV. So if that is nowhere near that, then we're safe using this. So I'm just going to take 0.5 times 1.67 e to the negative 27 times that answer I previously had. So I'm going to say control answer, and we'll square that. And that gives me 7.684 times 10 to the negative 12th joules. And now I can convert that by 1.602 times 10 to the negative 19th joules is equal to 1 electron volt. So I divide that by 1.602 e to the negative 19. And this one give me 47.996 mega electron volts. So notice that is a good factor of 20 smaller than the rest mass of the electron, I mean of the proton. So yeah, we're safe in using classical physics. I would say we're right on the cusp. You might get a slight difference by calculating the kinetic energy relativistically, but not a huge difference. Okay, so I would say that's sufficient. Any questions on that? So now you see how we can use those cyclotron equations and stuff like that. Beyond that, let's change this back for a second. Hopefully everybody's got this stuff written down. So I'm going to kill that camera view. So beyond that, it was discovered that that's not necessarily the best way to accelerate a particle, because for starters, one of the fundamental rules that came out of Maxwell's equations was that charges, when charges are accelerated, they actually radiate energy. And because they're radiating energy, you just can't make energy from nothing. That's stealing kinetic energy from the particle. Okay. And by stealing kinetic energy from the particle, you're defeating what you're trying to do, which was give it more kinetic energy. So that radiation that was given off is called synchrotron radiation, because it's basically in sync with the particle as it goes around the circle. So they came up with other ways as well. They, for instance, considered linking up the frequency in such a way that the particle could behave or could accelerate a little less weirdly, or excuse me, could accelerate a little less energy efficiently way. Sorry, bad words there. So anyways, they figured out other ways to do circular accelerators, but they all became a problem. And in fact, the linear accelerator was the one that wasted the least energy, but you're still accelerating particles. That's the nature of the game. You got to accelerate them. So you're going to have some radiation loss either way. They made something called a synchrocyclotron, where you could actually link up the magnetic fields, because eventually when you get it going so fast, it actually does create a velocity that the kinetic energy depends on the velocity, more so than just 1/2 mv squared. It's got that gamma mv squared, so the frequency is going to actually be changed. So you don't have that cyclotron frequency that's a constant. As you get higher and higher, you reach into relativistic speeds where the kinetic energy and of course the momentum both have a different dependence on V's that don't cancel out. So the faster it goes, the more you have to alter the frequency. When they discovered that, they managed to hook up a frequency device that could change the frequency as it went around the circle. And that was called a synchrocyclotron. So that's the next generation of circular accelerators. And then they also had multiple circular accelerators where they could put particles going in opposite directions so that you get sort of twice the energy. If you bring them both up to 1 giga electron volt, then the sum of the two is going to be 2 electron volts, and they collide head on that way. You can even put rings, rotating rings, if you will, where you can have a particle accelerate and then it just pops out at the instant you need it to, so it can accelerate with something else. And then you even go on to linear accelerators. That's where we got, for instance, the SLAC, the Stanford Linear Accelerator Center, I suppose is what the C means. And in that case, you have little tubes that are, polarized to some voltage so that a positive particle might be pulled into it, and then it changes. Just as it starts to leave, it becomes negative, and the one in front of it becomes positive. That pulls it through here, and slowly but surely you get it going up to a higher and higher speed. And that was basically the accelerators that we made. Now, the cool thing is this D's that Lawrence made is not necessarily used anymore for physics, but if you'd asked, someone at the time, hey, is this D system that you made up, is that going to be of any use to humans? Are we going to have any way of making a typical American's life any better? And he'd say, nothing I can think of. Well, it turns out now those D's are used to create accelerated particles to treat cancer, like you've probably heard about Hampton University's Proton Therapy Center. The proton is actually a really ideal particle for hitting certain types of radiation, specifically because it causes less collateral damage. So the energy spectrum that comes off from a proton is basically, as you go within the body, the energy is at a certain high level, and then it peaks, and then it drops down really rapidly to nothing. And you can adjust the energy level so that that peak lines up right in the center of a tumor. And then you shoot, say, if the tumor is like 3 or 4 centimeters below my belly button or something like that, I shoot from the front, I line up the energy so that that peak's lined up right at exactly 3 centimeters behind my belly button. And then everything between my belly button and the particle get a good dose of radiation, but that's mostly superficial tissue. It's skin and fat, and I would say it's probably a bunch of abs, but maybe there's some fat in there. And then the majority of the energy is delivered directly at the tumor, and then nothing behind it gets harmed. So that's a really ideal scenario. Whereas an electron sort of has this huge, and they're called Bragg peaks, has this huge wide Bragg peak. And it pretty much, if you get it centered on the tumor, the electron's going to do damage to everything before and after it in much more drastic way. So that's the advantage of a proton. And lo and behold, we get these protons from these double Ds, or these super Ds as they've been called. So that's a technology that we would not have suspected had any use for humans and for America and for Great Britain or anything like that. And lo and behold, after a few decades, we realized, yeah, it does. We can use that now to make that. X-rays are made by similar type devices, not these, but they're made by devices that create electromagnetic radiation, so on and so forth. So in reality, sometimes just pure research gives you things that you didn't know. And your book talks a little bit about actual interaction between a scientist and a senator or something along those lines, where he explains to him that what he's studying doesn't necessarily give anything to the security of our nation, but it gives things to everything that makes our nation great, specifically the fact that our nation got to a more than subsistence, so that we can now create art and music and poetry and study science. And that's what's worth fighting for in their sense. So that's kind of neat. All right, now that we've gotten through that, and I've talked about how the different accelerators can actually be used, we can talk about, for instance, the Large Hadron Collider. You can see pictures of the Fermi Lab and CERN, which is where the Large Hadron Collider is, and stuff of that sort. But you might want to know some things like, well, what about when we get electrons to really high accelerator speeds, to like 90% of the speed of light and all that stuff? what then is the kinetic energy, what then is the work done, and so on and so forth. So you can, you know, solve problems like that with just basic work equals change in kinetic energy, the work energy theorem, right? And so you calculate the work as the change in kinetic energy. So if you want to know what the work done is, you take the change in kinetic energy, which is the final kinetic energy is going to be gamma minus 1 mc squared, where m is the mass and c is the speed of light, and gamma is that 1 over the square root of 1 minus v squared over c squared. So if you put in 0.9, you get one value. If you put in 0.99, you get another value. You put in 0.999, you get another value. And you'll see that that work done gets huge, just going from 99% of the speed of light to 99.9% of the speed of light. It's a huge, huge difference. So those are all easy things that you can do. One example is, what is the speed of a, let's say, 2 tera electron volt proton? So let's do that. We only got about 4 minutes left, so that's about all we can fit in anyways. So what is the speed of a 2 tera electron volt? I think this should go over here. 2 tera electron volt proton. And I believe this is example 3. Okay, so what we're seeing here is 2 tera electron volt is the kinetic energy. So K is equal to 2.0.
Are you supposed to be seeing something?
Oh, yeah, you probably are, other than my head, right? Thank you. I wrote down a question. What is V, the velocity, for a 2.0 tera electron volt proton? And if you're rusty on your prefixes, you know, giga is 9, and you should know that this one's 12. But if you also look in the front cover of your book, you'll see that tera is 10 to the 12th, and that is 2.0 times 10 to the 12th electron volts. Whenever they say a energy of a particle is such and such, they mean the kinetic energy, not the total energy. Okay. We also know that E squared is equal, well, excuse me, let's not do that one. Let's do kinetic energy is equal to gamma minus 1 times mc squared. Well, what we know about the proton already is the proton has a rest energy, mc squared, equal to 938 MeV. So we already know this part right here is 938 M, that's big M, EV. So we can actually just take K over 938 MeV is equal to gamma minus 1, and then we just add 1 to that, and we say gamma is equal to K over 938 MeV plus 1. But of course, gamma is equal to 1 over the square root of 1 minus V over C squared. So then we solve for that. So let's go ahead and get this part. So I'm going to say gamma is equal to 2.0 times 10 to the 12th EV over 938 times 10 to the 6th EV. And then I'm going to add 1 to that. So I'll take, again, you could actually do the regular math and use joules and all that. This is just an easier way because I already know it. So it'd be 2e to the 12 divided by 938 e to the 6. And I get 2.132 times 10 to the 3rd. So that's 2,132.2 plus 1, which maybe you'll call 2,133.2. Okay, but to be honest with you, you only had 2 sig figs, so all these are extra crap anyways. So that's what we get for gamma. Now we just have to say, well, wait a second. If I square both sides of this, I get gamma squared is equal to 1 over 1 minus V over C squared. And then I can say, okay, well, 1 over gamma squared is equal to 1 minus V over C squared. And then I can say, okay, well, if I add v over c squared to both sides, then I'd get, and subtract this from both sides, I get v over c squared is equal to 1 minus 1 over gamma squared, which is gamma squared minus 1 over gamma squared. Take the square root, and I get v over c is equal to the square root of gamma squared minus 1 over gamma squared, which is just the square root of gamma squared minus 1 over gamma. Okay. And that's really all I need, is that fraction of the speed of light. And then I can just, state it that way. So now I'm going to take the gamma that I just got, and I'm going to square it, and I'm going to subtract 1. So I'll say square minus 1. I'm going to take the square root of that, and then I'm going to divide it by, again, that gamma. And that gives me 0.9999999. That's 7 of them showing to me. So it's definitely more than 99.99% of the speed of light. Any questions on that?
No.
If I tried to multiply that by 1, my calculator will show all the digits. So I'm going to do that times 1. Notice it says 99999989. 99 was 1, 2, 3, 4, 5, 6. 6 nines followed by 8, 9. So it's it really could go pretty much a little bit beyond here, but this one would become an 8 and a 9 and then a 5. So that's it. That's enough for today. We're about 2 minutes beyond the time limit. So you guys are free to go. I will be posting this pretty soon, hopefully today sometime. And you guys can see it on my YouTube channel. Remember, if you don't remember it, it's www.youtube.com/Billy Younger Physics. This is Younger, my last name. Physics Solutions. Actually, all these are lowercase, by the way. It's just the B, Y, P, and S are capitals. Okay. Have a good one. I will see you guys either in lab. Well, actually, I do see you tomorrow in lab, don't I? Or maybe Thursday. I see you in lab. That's it. And I'll see you again in class Thursday. I'll wait for the last person to leave in case anybody has any questions.
Thank you.
Questions on the homework.
Go for it.
Mind if I share my screen?
Yeah, let me make sure that you can do that. Wrong button. So exhausting. Okay, now you can.
Can you see that?
Yes.
Okay, sweet.
The crap is all that.
What was that?
I don't know why I had all those up there though.
All the
Are they individual courses or something?
Oh, these are oh, that was the course evaluations I was filling
Oh,
out.
okay, gotcha. No problem.
So this is for the homework. I think you might have said that the chapter 15 was due Wednesday.
Mm-hmm.
But it
Yeah,
says
I was going to ask about that too.
yeah.
Yeah, so that one was supposed to be, you mean December 1?
Yeah, December 1st, I think, was supposed to be the due date for chapter.
Okay, I'll fix that. I thought I did that Friday, but clearly I didn't. I'll change both of those, homework and conceptual.
Okay. So on the conceptual, there's the last section here.
Mm-hmm.
It's talking about let me close this out. At which 3 points x1, x2, and x3 closest to x equals 0, both x greater than 0, will the displacement of the string be 0 for all time? So it's asking where the nodes will be.
Okay, so what was your equation up above that you ended up discovering? Is that it, the A cosine kx?
Yes, sir. So yes, sir. The equation is A cosine kx sine omega t.
Okay. So so what you're saying is the change in space is a flat cosine function. So that means that, you know, it starts off at 1, or A, that is, goes down to 0 at pi over 2, and then goes to negative A at pi, and then back to 0 at 3 pi over 2, and then back to pi at 2 pi. So what they're asking you here is at which 3 points, x1, x2, x3, closest to x equals 0, but at x greater than 0, will the displacement of the string be 0 for all times? Ooh, okay, for all times now. Okay, so that has to be that, right? So yeah, so everywhere that cosine is 0, so cosine is 0 at pi over 2 and 3 pi over 2, and then the next one would be 5 pi over 2.
Yes, sir. So in order for cosine to be so kx would have to equal pi over 2, correct?
Yes, yeah, kx would equal pi over 2, so the x would be, and k is 2 pi over lambda.
Okay.
So x would have to be, the total thing, k times x, would have to equal pi over 2, 3 pi over 2, and 5 pi over 2. So if you want to work it out that way, it might be asking you in terms of, yeah, it's asking you in terms of the wavelength, isn't it?
Yes, sir. So you also end up with, oh, I see. Okay. So if you have kx equals pi over 2, just for this would be x1, you would have 2 pi over lambda times x equals pi over 2. The pi's would cancel out. And then that would be 1 over lambda times x equals 1 over 4, which means that x equals
Lambda over 4, lambda, 3 lambda over 4, and 5 lambda over 4. Is that what you're getting?
I got lambda over 4 for the first one, and if you see here,
just put a lambda to the right of that, and that should be your first answer. And then
it has the lambda
okay, gotcha.
already
So
there. I
then
made that mistake earlier.
Comma.
So it would be, and then 2 over 3.
I got 3 over 4 for the second one,
Okay.
and I got 5 over 4 for the third one.
Okay.
If you want to look at the paper for a second, stop sharing for a second. You can look what I did. The general response.
Oh, I see.
You see? Can you see that? Okay, so that.
Yeah, I didn't know that you were writing stuff down.
Oh yeah, I was just doing it to make sure I was doing it right in my head. So, yeah.
Okay.
And that said, it did say it was correct. So that's cool.
Yeah. Okay, I see that. That makes sense. And the other one was the exact the other one on the conceptual. I still have like 2 more questions. If there's anyone else that's like in a hurry that needs to ask, that's okay.
Anybody else have a question?
Just a quick question about the final exam. It's just everything we've learned so far, right?
Yeah, and it may or may not include 43 and 44. But,
Okay,
I'm leaning towards not.
when do you think you'll post the practice final, if you have
I'll
one?
probably be posting that sometime this week. If
All right,
not,
cool.
definitely by Monday of next week.
Is it the 2 weeks from now? It's the final?
Yeah, roughly. It's like the 17th is the last day of the week, and I think the 13th was the day we I chose to make the final on, whatever the Tuesday is of that week.
Okay. I was asking about the midterm thing because I don't know about this final. I mean, I felt good about the midterm. I was good at that, but I was just, these last few chapters have been kind of kicking me in, especially work.
Yeah, I get you. It's Well, like I said, I don't have a way of doing the other way. You know, your final exam is going to be your final exam grade. But if your midterm is better than your, or if your final exam is better than your midterm, I'll replace that. So I can't do anything the other way. But still, just focus on those practice final exams, and that'll be good. I'll try to get it done earlier for you though.
All right, thanks,
Okay.
Professor.
And just to double check, the final exam, the practice final exam would be like the final exam.
Yeah. I usually take the same bank of questions.
So you think if you do it 60 times, eventually you'll do good like I did last?
Yeah, doing it 60 times probably will mean that you've seen maybe all but 20% of the points on the final exam.
Not true. Even around the last 10, I was still seeing new questions.
Yeah. I mean, what I'm saying though is there's a high likelihood that you'll have exhausted the ones that I'm actually using for the final, at least 80% of the points of it.
Okay.
I frequently add 2 questions that are brand new on the final. If it's a 10 question final, if it's a 20 question, I might ask 4 or even 5.
Okay. Thank you, Professor.
No problem.
All right, y'all have a good day.
You too.
Thank you, Professor. Have a great one.
You're welcome. Thank you. So what are we doing with the Desmos and all this stuff? Oh,
So this was the other one. So you have a wave equation right here.
mm-hmm.
You have their equal waves traveling in opposite directions.
Okay.
You'd end up with so anyway, then it's asking, so you have the y1 plus y2, this is y1 over here, and y2 is the same except for this is a positive right here.
Right.
And that equals ys, and it's saying ys has 2 functions. It's a function of x times a function of t. So I got, and I checked it with Desmos earlier, I got a sine, or my equation that I ended up with for ys was this, is 2a sine kx cosine omega t.
That seems right.
But it's asking for y of x and y of t as separate equations. So the previous answers I was doing it, so I had y of x being a sine kx and then 2 cosine omega t. This one was the one I thought would be the most correct because it's applying the amplitude to both the function of position and the function of time. Anyway.
This is chapter 15?
Yes, sir.
And you're looking at this problem 15 homework, and you're looking at creating a standing wave. Let me look at it. They might be asking for something that's sort of specialized, so it's hard to see from that box. So let me look at my side and see if I can figure out anything about that.
Sounds good.
I'm going to pull it up real quick. Opening this up now. Slow process.
Oh, you're fine.
Okay, so I found the problem. Gotcha. And you're on part C, if I'm not mistaken, right?
Yes, sir.
Okay, so let me look at your answers real quick, because you said you already submitted.
Yes, sir. Here are the previous answers.
Okay. That first one looked pretty good. Let me see. Okay, I think here's the problem. It doesn't like you, and it's not fair to do this. It doesn't like you separating the 2 and the A. So if you would have done the 2 and the A both on the sine in the first answer, it would have given you right. If you did the 2 and the A both on the cosine and nothing on the sine in the second answer, that would have been graded correctly. So
so something like this with 2A sine. Is that what you're saying?
yeah, sine kx and then comma cosine omega t. Yep.
Okay.
So yeah, that was a pain in the butt. That should yeah, they should have been a little. Express your answers in terms of a, k, x, omega. Separate the 2 functions with a comma. Yeah, they didn't really give you enough information to understand how they expected the notation, because you could assume the a would go with the cosine and the 2 would go with the sine. That seems fairly reasonable to me as well. But yeah, that's
yeah. Yeah. So I had one more question.
okay.
And that was with this year, they're asking you to basically take the partial derivative with respect to t, is my understanding, and to plug the values. So the partial derivative with respect to t would be 44 times 0.15 cosine 0.38x minus 44t, correct? Because you treat x like a constant.
Yeah, but don't forget you get a negative because the negative in front of the 44, and then the derivative of sine is cosine, so that's a positive. So yeah, don't forget the negative, in other words.
Okay, so for this, I just want to make sure I didn't maybe I fat fingered something, but so I'm just plugging that in real quick. Okay, and on.
So yeah, I think the problem right now would be a negative sign.
Okay, so yeah, because so this should be negative, but so I got negative 2.08 just on that last time I plugged it in. So we'll see if that's it.
Let me see, hold on before you. Okay. Yep.
There we go. Okay. So yeah, I think I must have just forgotten to do a negative. And I think that's all my questions.
That's cool. Looks like you're really done then. Good job.
Thank you. I appreciate it.
All right, I will change those chapter 15s to December 1st. So,
Sounds good.
all right, see you, man. Have a good one.
You too.
Bye.